Chapter 4 is talking about the network access layer of the TCP/IP model. So the very first layer of that model. We're going to talk first about some physical layer protocols. So there's some different types of connections to be able to connect to a network. And what you're seeing here is some of the common equipment that you probably have in your house that allows you to be able to do that. So internet can be wired or wireless, or actually both. Because if you look at the back of a router, what you see in that little 4 ports is actually a very small switch in the back of that router that allows you to either get wireless signal from the router or be plugged into the router. And almost every router has something like that to it, so you can have a wired and a wireless connection with your internet connection. And there's someone that's plugged into port 3 into the laptop to make a wired LAN connection. The network interface card is used to connect the device to the network. So a NIC can be either wired or wireless. A wireless NIC is going to receive wireless signal. A wired NIC is going to have a cable plugged into it. So how do you know which one of those to use? A lot of times it depends on the situation. The farther a wireless laptop gets from whatever's supplying wireless signal, the slower and slower and the less fidelity that signal will have. So if it has to share wireless in the building with all the other wireless computers, that may be a performance issue. But a wired computer has a solid connection that's always pretty much stable. So depending on the environment is what you would pick wired or wireless connections. There are some businesses that I've encountered that maybe they're in a historical building, so for whatever reason they cannot alter the structure, which means they can't drill into the walls and drop cable. So in that instance, they kind of have to have a wireless connection. There's business I've encountered that their office was really close to the hospital. They wanted a wired connection, even though that we told them that probably wasn't a good idea. There was so much interference from the hospital, their signal was terrible, and it would drop multiple times a day. So again, it kind of depends on the situation as to which one you would choose. So the physical layer is the layer that transmits the bits across the media. So the media or the carrier could be wired or wireless. We're going to talk about the different kinds of carriers on the physical layer. This is the stuff that we're most familiar with because we know what those blue cables are that are hanging out the back of the computer, right? We're familiar with what that looks like. So this is all on the physical layer. There's 3 forms of media on the physical layer. All 3 of these types are governed by these standards organizations. We kind of touched on those last week. There were a whole bunch of different ones and they all kind of had different jurisdictions. But you can have electrical signals, those come from copper cable. You can have light signals, those come from fiber optics. And then you can have microwave signals that come from wireless media. So the TCP/IP standards are implemented and governed by the IETF. There are several different standards organizations that deal with things on the physical layer. The ISO, the EIA, TIA, that's the one we commonly see. We'll talk about that in a minute. The ANSI, IEEE. The physical layer addresses standards in the 3 kind of functional areas. They go into a lot of detail about this in Cisco Academy. I want you to kind of have an idea of what they are. The first of them is the physical components. So that's the hardware, the media, the connectors on the end of the cable that transmit and carry the signals back and forth. So that's the NICs, the interfaces, the jacks on the end of the wire, the design of the cable that the standards have dictated. This is the way we're going to do things. Then there's encoding. Encoding is converting a stream of data into this predefined code into these 1s and 0s so they can be transmitted. So grouping them up in patterns, we're going to talk about how they do that. So that's a pattern of voltage or current that's used to represent bits. So 0 is off and 1 is on. That's what encoding is. The classic thing you hear about when you hear about encoding is Manchester encoding. So it represents 0 by high to low voltage transmission and 1 from low to high. You need to understand Manchester encoding. If you see that graph, You can see that it ends up in the middle. It's a stair step, but the ones and the zeros are determined by where it is in the middle of the path. And then there's signaling. So the physical layer has to generate this signal. It's electrical, it's optical, or it's wireless. That's the three media that we do this with. They're the ones or the zeros on that, and whatever method gets us that we call the signaling method. So maybe a long pulse is a 1 and a short pulse is a 0, but there's some way to distinguish between a 1 and a 0, a bit pattern moving across the media. So that can be used. There's an example of frequency modulation and amplitude modulation. I'll let you read more about that on Cisco Academy. Bandwidth is how we talk about data transfer. We generally use the term bandwidth and throughput, and they mean a little bit different things. So bandwidth is the capacity of a medium to carry data. So how much data can flow from one point to the other point in a given amount of time, and we normally measure that in seconds. So bits per second, kilobits per second, megabits per second. Like when we talk about the internet speeds we get at our house, we probably talk about megabits per second. And that equals 1 million bits per second. So get used to seeing that. That's 1 million bits of flowing every second, which seems really high until you try to use it, right? Bandwidth is largely determined by what type of media that we use. Throughput, however, is the measure of the transfer of bits across a medium over a given amount of time. So throughput and bandwidth are not necessarily equal. You may have quite a bit of bandwidth, but because lots of other people are using the line, your throughput decreases because everybody else is sharing the same wires, essentially. When you get home at night, everybody gets on Netflix, right? Netflix or Hulu, they start streaming things. So you see the whole throughput kind of the neighborhood kind of decrease because everybody's using the bandwidth. Something like 25 or 30% of all internet traffic is Netflix in the United States. It's pretty amazing. Latency is created by the number of network devices encountered between the source and destination. So the more points that your data has to move, the more latency you might have. This is a website that's used to measure throughput. Does anybody have any sites they use? When your internet's slow, do you go to a website and see how fast your internet's running? What are those websites?
Speedtest.net.
Speedtest.net.
AT&T speedtest.net.
AT&T has a speed test.
Leapfrog.
Okay. Speakeasy is another one. I actually had a student introduce me to Speakeasy. And I'll pull that up real quick and let's look at it. But one of the things that's interesting about it is it doesn't just do one speed test, it does multiple speed tests. So I'm going to do a test like I'm connecting to a Dallas location. So obviously since we're at the school and they have pretty good bandwidth, we're going to see higher things than we would see at home. But it's going to do multiple tests and kind of take an average between them. So it gives you a little bit more information. And it takes a little bit, so I'm not going to let it completely finish. But it's sending a packet to a server in Dallas, and then Dallas is sending a packet back to us to determine the upload and the download speed. So here we have 26.03 megabits download and 67.09 upload. So that's pretty darn fast. So there's another one that I think gives some good information. Looking at some types of physical media, so this is a Cisco router we're looking at. Characteristics of that kind of media would be the type of the copper cabling that we use, the bandwidth that we talked about, the different kinds of connectors that can be used. You can see there's lots of different places to plug in here. The pinout and the color code, and the maximum distance of the media. So let's talk a little bit about that network media. So first off, copper cabling. Copper cabling is by far the most used because it's cheap. You can go to Lowe's and buy 1,000 foot of copper cabling for $70. So you could do quite a bit of cabling just with one box. Now, the main problem with copper cabling is that it can only go about 100 meters. So your Cat 5 cable that we're all using in this room to connect only goes about 100 meters. And that's 330 feet for those of us that did not grow up understanding the metric system. So a problem with copper cabling is it's pretty susceptible to what we call electromagnetic interference. So other waves bouncing around might actually make the signal degrade or drop completely. That means the computer could get the wrong information, or in some cases, no information at all. So sources of electromagnetic interference would be like fluorescent lights. We have to use a different kind of cabling to run over fluorescent lights for that reason. And maybe an electric motor would give off some sort of interference. They're also susceptible to what we call crosstalk. So that signal between two wires that are close together crossing over to the other wire, so the information gets sent out the wrong places. That can be caused by electric and magnetic fields as well. Two telephone wires are together, the person on one end might switch conversations essentially. To counter this, we wrap the cables up in a shielding. The shielding helps us be able to fight that interference. There's three types of copper cabling. We have unshielded twisted pair, by far the most popular. That's the $70 stuff at Lowe's. We have shielded twisted pairs, a little bit more expensive. And we've got the coaxial cable. So let's talk about those. Unshielded twisted pair has 4 pairs of color-coded wires. They're all twisted together. They're encased in this outer jacket, this flexible plastic shielding that protects them from minor physical damage, like being stepped on and things like that. The more the wires are twisted, the less likely the interference is. And the connector on the end of this is the RJ45. We're going to be putting those on in class. So here we have what the unshielded twisted pair looks like. We're going to work with those up close and personal in this class. The shielded twisted pair is really similar to the UTP, but they've added extra shielding inside of it. That's what keeps it from being so susceptible to interference. So each pair of wires is wrapped in a foil shield, and then all the pairs of wires are wrapped in another foil shield, so that they're less likely to have crosstalk and be susceptible to interference. Shielded twisted pair is certainly used too, but if you're in a high interference environment, you might choose that over the cheaper stuff. Coaxial cable is what we normally see coming in from our cable TV provider. They use coaxial cable. So there's a copper conductor, that's what's in the middle, that's actually what transmits signals. There's the flexible plastic insulation that coats that. Then there's an insulating material that kind of looks like it's woven. It's copper and it's woven, and that's supposed to keep interference out. And then there's a cable jacket all the way around that. You've got 3 different kinds of coaxial connectors, but by far the F-type is the one we actually see used. The other ones are a little bit older. When it comes to safety with copper media, cables can be fire hazards because the plastic sheathing around the cable is flammable. So we have to take that into account. Voltage is running through these cables. It's essentially electricity that could possibly be flammable. So they have to be installed properly to keep damage from happening to the devices. We have to inspect our insulations. Our equipment needs to be grounded so it doesn't cause something to flow through the cable. They need to be connected correctly. And again, depending if you're running over fluorescent lights, you wouldn't want to use the cheapy UTP cable because it might be able to be caught on fire. We use what's called plenum cable if we're going over that, which is a little heavier grade. So some properties of UTP cabling. There's, again, no foil, no shielding, and we have these color combinations that you see here. So we normally refer, starting at the top, brown, brown, white. The cables that you're going to be using in my class, the colors are bright like this. Sometimes you can go by cable and the colors are kind of muted and it's hard to tell the difference. Do I have anybody colorblind in here? One person?
Sometimes.
Sometimes? Okay. We'll have to work on that because as you can tell, color is probably going to be an issue here when we go to put ends on cables, but I have a cheat for it. So brown and brown white, green, green white, blue, blue white, orange, orange white is how we refer to those pairs within that cabling. There's different categories of cable. That would include different cable types, lengths, connectors, the way the cables are terminated, and how we test the cable. In UTP, the higher the category, the more bandwidth they can carry. So you would use Cat3 cable. It's really low speed. You might use it for a phone connection. But you would probably be using Cat5e or Cat6 for a data network like this because it has a higher throughput. You can use something faster, but the cable is probably going to cost a little bit more. So it depends on what the organization is willing to pay for. There's more types than these, but these are the actual common ones that you would see when you're out in the wild working as a net admin. The plugs that go on the end of the UTP, we have the RJ45 plugs. Those are the ones we'll be using in class. We have the RJ45 UTP socket. I call it a keystone. That's the thing that's in the wall, right? So you've got a connection with an Ethernet cable from the NIC in your computer to the keystone in the wall, and there's a connection from the keystone in the wall to the server rack in the closet. That's how you're getting connectivity in here. So when cables are made incorrectly, performance can be affected in the end. The end might fall off. You might have a poor connection. Not all of the wires are touching all the pins, so maybe it won't work. So we have to be careful, and you've got some example down there of a bad connector when the wires are exposed, things get all untwisted. It's not covered by the sheath. When you crimp down an end, like we'll do in class, you're actually crimping this little block within the RJ45 jack down to the sheathing of the cable. So when you pull it, it doesn't come off. We'll go over that when we go over making cables. You need to memorize the color combinations for the cabling because you're going to need that not only in this class but for the rest of your IT career. You can learn how to program Cisco, everything, and have all the certs you want, but if you can't make a cable, it's not going to go well, right? So we want to go ahead and do that here in the fundamentals class. A straight through cable is T568B on both sides. So to the right you see the T568B color combination, which is orange, white, orange, green, white, blue, blue, white, green, brown, white, brown. So that is the way that you would place the wires. You straighten them out, cut them so they're even, and place them into the jack in that order. So that is a standard. Not everybody follows that standard, but that is the standard for a regular straight through cable. If you went and bought one at Walmart, that's the way the colors would be lined out. A crossover cable is T568A on one side and T568B on the other. So we'll talk about why that is. The pins that transmit and receive switch on a crossover cable so the devices can talk to each other. Out of all these 8 wires, only 4 of them actually move any data. So the greens and the oranges are the things that switches. So your green, white, green, and your orange, white, orange switch between A and B, and you need to know that. The reason is so that like devices can talk to each other. So when you're looking at when to use a straight through versus a crossover, if 2 switches are talking to each other, they need a crossover because they're the same kind of device. If you're looking at what about a PC to a switch, those are different kinds of devices. So they just need a straight through cable. And that is something that you will need to know. Remember that crossover cables are for like devices. You can test UTP cables. We'll be doing that this week, either through a wire map, testing the length of the cable, testing where signal loss begins, or testing for crosstalk. We're going to test and figure out, I've made some bad cables for you and you're going to tell me what's wrong with them. Some things that you would see out in the field. Now on to fiber optic cabling. Fiber optic cabling is used for long distances, even miles of distances. Because it uses light to transmit, it's not affected by electromagnetic interference or radio frequency interference because it's light. It doesn't have anything to do with electrical current, so to speak. So inside the cable is strands of glass about the size of a human hair. And here's what the inside of that cable looks like. The fiber strands are in what's called the core, right in the middle of that. The cladding is around that and it's reflective like a mirror. So essentially you have a tube with a bunch of light bouncing around inside of it. to make the fiber optic media. There's two kinds of fiber optic media. There's the single mode fiber, which the core is really small. There's less dispersion. So think about a paper towel tube that's got a reflective mirror inside of it. In this case, it's a really, really small tube. So since it's small, the light doesn't have a lot of places to bounce around and refract and reflect inside of it. So it tends to go further. That's why single mode goes further. Now, it has a straight single path of light, so it can go for miles and miles. The multi-mode fiber, the core is bigger, so there's a lot more bouncing around inside between that light. So the light bounces around inside the cable. That's called dispersion. The more the light disperses, the greater the chance that the signal gets lost. So multi-mode fiber is really meant for shorter applications, like from the admissions building to this building. Maybe not for miles and miles. There are different kinds of fiber connectors. You need to, in general, know what these are. I can tell you when you get to Net Plus, this is going to come up again. But there's the ST, the SC, the LC, and the duplex multi-mode LC. If you can think of something that makes those names distinguishable to you, so I would always say like ST stands for stick twist, because there's a stick on the end and you twist it to make it work. SC, square connector, it's the only one that's got square on the end as opposed to like a rectangular connector. LC for little connector, because it's the smallest one. And then there's the duplex multi-mode, and it's the only one that's got two ends going into a single. So if you can kind of remember that, that might help you on a test. We're not going to make fiber optic cabling in here. There's whole certifications and whole classes to be taken on just doing fiber optic cabling. And normally if you're an internet service provider, you might actually do that. But in a lot of cases, that's not something a net admin would normally do. So we're not going to touch that in this class. You need really expensive equipment to be able to test those things. Fiber optic cables, there's not a lot of wiggle room. They have to be done just right or they just flat out don't work. So we're going to leave that to the experts with all the fiber optic certifications. So here's kind of a chart for fiber versus copper cabling and what the difference is. So fiber optic has a higher bandwidth. It's got a high immunity. It's completely immune to EMI, radio frequency interference. Different safety precautions and the converter cost. So that's when you look at the difference between the two, there's quite a bit of difference. Wireless has some areas of concern, which we've touched on a little bit. Coverage area, certain construction of buildings may lead to not being able to have signal. Interference, which we talked about, the business that was close to the hospital and all the interference kept their wireless from working. Security, since it's everywhere, anybody within range can get to it. So we have to take some safety precautions when setting up a wireless network. And it's a shared medium. So a wireless LAN operates in half duplex. That means you can only send or receive at the same time. Now newer wireless standards are working to combat that, but that means the more people are on the wireless, the more the wireless slows down, and I know we've all experienced that. Who knows what Wi-Fi stands for?
Wireless fidelity?
Wireless fidelity, exactly. So that is one type of wireless media. Then we have Bluetooth. So Bluetooth is limited to about 30 to 33 feet. It's what we call a personal area network that we talked about in Chapter 1. So for example, I have Microsoft Sync in my car. It connects to my phone through Bluetooth so that I can talk hands-free. It's really cool. Then I have WiMAX. That is wireless broadband internet access. There's a local company called Zoom Broadband. They sell WiMAX. So if you've ever worked with them, it's the same thing as having cell phone reception. Essentially, there's towers that give off WiMAX signal. You have a device that grabs that signal and lets you get on the internet with it. But those are all examples of wireless technologies. To get wireless capability, you need two pieces. You need a wireless access point or a router that gives off the wireless signal, and you need a wireless NIC of some sort that receives that signal. So when I was working in my shop, I would have all kinds of people that would come in with a desktop computer and they would say, I bought a router, I don't understand why my tower won't work wirelessly. And most of the time it was because they didn't have a wireless NIC to grab on to that signal, which is an easy problem to fix, but it's important to know there's two pieces to being wireless, something that gives a signal and something that receives it. You've got to have both, and they've got to be configured. So a little bit about the data link layer. We're kind of focusing on layers 1 and 2. So what does the data link layer do? It allows the upper layers to access the media. It takes packets from layer 3. It takes packets from layer 1, where we talked about encapsulation and the video of the guy taking off and putting on different hats. So it receives and directs packets from layer 3, and it performs error detection. So let's talk a little bit about the data link layer. It's the only layer that is divided into 2 sub-layers. That's going to be a test question forever. Lots of different classes. And those 2 layers, the LLC sublayer and the MAC sublayer. So LLC stands for Logical Link Control. So this is the thing that allows the layer 3 stuff to utilize the network card. So this allows the network card to have an IPv4 address so it can do something on the network. Then the MAC, or the Media Access Control, this is the hardware processes. This is what gives it a MAC address. So it's a physical thing. And this kind of illustrates how these things work together. Wired satellite and wireless media can all carry data in frames because frames is a standard. We'll talk a lot about standards in this class, but a frame is the same thing no matter who's carrying it, along what medium. The frame stays the same. In this case, we've got a wired network going to a router, talking to satellite dishes in space, but it doesn't matter because it's all a frame and it all understands what a frame is. It also provides access to the media. It controls the transfer of frames across media. So across these 2 routers, for example, that are connected with a serial cable. These are some of the companies that define the standards on the data link layer: IEEE, ANSI, ITU, and the ISO. The ISO may be OSI. That might help you on the test. All right. Getting towards the end, let's talk about media access control. So when we're controlling access to the media, we have 3 different kinds of media we've discussed. We have to make sure everybody can access it. Yes?
So I did have a question.
Okay.
That kind of confused me. So a packet is made up of multiple frames, correct?
It's generally 1 frame. Generally
But it's
1.
multiple segments.
There's multiple parts of a frame, but it
Right.
generally just has 1 packet's worth of data.
Okay.
And then when the data gets too big to fit in that, they break it up into multiple packets.
Okay. Okay. All right. Yeah.
Good question. So these 3 computers are connected. They all want to send and receive data. They all need to make sure that they can access the media. In this case, it's a wire, but it could be anything that we've talked about today. So the actual media access control that's used in this instance depends on the topology and the media that they share. So the topology is how these things are connected. And the media sharing is it point-to-point like a WAN connection? Is it shared like in a LAN network? And this looks more like a LAN, but the shared media that they've chosen here is just plain old wire. We've got 2 different kinds of topologies to talk about. The first one is physical. So this is the physical connections between devices on a network. So router switches, wireless access points, how are these things all interconnected? They're normally a point-to-point star connection. You can kind of see that the router tends to be the star right there that goes to the center of the star, I should say, and everything is connected to it. So these are physical connections. You can see they're kind of divided up by room. We've seen a graphic like this before in this class. So that is a physical topology. So at TSTC, the physical topology is how the computers are placed in the rooms. Generally, there's a switch in the room that all of them connect to, and then that switch connects to the infrastructure. So that's our physical topology. The logical topology is the way the network transfers frames from one node to the next node, or one client to the next. So there might be virtual connections that are listed here, but if somebody on the Purple network wants to talk to the web server, where do they have to get? What do they have to talk to get to the web server if they're on the Purple network? Which is one laptop right now. What are the devices they have to go through?
They go through a switch, a router, and another switch.
Yes, switch 4, router 1, and switch 1. So logically, those are all the points at which those nodes have to talk to each other before you can get from client on the Purple network to the web server. That's an example of a logical topology. Common WAN topologies to talk about. Point to point, connecting one point to another point. That's it. This is really popular technology. So let's say there's a business on one side of town, they have another branch on the other side of town, and they're connected. That's just 2 points with a connection between them. There's a hub and spoke. So this is a WAN version of the star topology. There's a central site, and let's say different branches within that corporation reside, and they all talk to the main branch, like banks. Let's say there's one main Chase Bank and a whole bunch of other little Chase banks, and they're all interconnected. Then there's the mesh. The great thing about the mesh is that there's a lot of availability to it, because if one link breaks down, there's a whole bunch of other ways to get from point A to point B, so it won't really interfere that much. But you've got to run a lot of wires, right? Every one of those things is a wire that's interconnecting different points. So that means a lot of wires have to happen. So there's a variation of this called the partial mesh, where we don't completely interconnect everything to everything else, but we have maybe some really important people that need to talk, and they've got more than one connection to each other. So here's what the physical point-to-point looks like. It's a dedicated connection. They don't have to share their resources with anybody. It's not like they've got to share with all the other businesses on the block. They have one point-to-point connection between node 1 and node 2, and they have it all to themselves. A logical point-to-point is adding points in the cloud, right? Adding points in the internet, so to speak. So one router talks through the internet to get to the other router. Logically, there are other places inside that they're going to have to talk to, but we don't necessarily know what they are, because a lot of times the internet service provider handles that. But since it's a WAN, like the internet, there's probably lots of switches and routers and firewalls and DHCP servers and other things within that cloud that are making all that work. Physical LAN topologies, you definitely need to know the difference between these. So there's a star topology, which is the most common one. There's one central, we talked about intermediary or intermediate devices like a switch back in chapter 1, and everything's just connected to that. So generally the switch is in the middle and everybody connects to the switch. It's really easy to install, it's really scalable. However many ports there are on the switch, that's how many people you can plug into the switch. And then when you run out of ports on the switch, you buy another one, and then you plug more people into it. So that is the star topology. And when you add another switch in, they technically call it the extended star. So you've got multiple switches plugged into each other. The bottom two are what they call legacy systems. Legacy is a nice way of saying it's old and we don't use it anymore, but they call it legacy. So there's the bus. So all of these systems are kind of chained together in this bus style. They all have to share the same line. Hubs use a bus topology, and they have to terminate on each end because the signal propagates out all the way through the end of the wire. So they have to terminate it on the end to say, stop talking, no one's listening, basically. And then there's the ring. End systems are connected to their respective neighbor, and it kind of forms a ring. The ring doesn't need to be terminated because it's a ring, it doesn't ever end. But the problem with the ring is generally only one person can talk at a time, and you have to wait your turn, and it makes things really slow. Something that comes up in this chapter is half and full duplex communications. With a half duplex, you can send, you can receive, but you can't do both at the same time. It's like using a walkie-talkie. You can talk or you can listen, but you can't do both because that's just not what a walkie-talkie does. A full duplex connection means you can send and you can receive at the same time. So our modern switches are like that. We can send and receive data at the same time. When we talk about media access control, we talk about contention. So in this hub topology, we've got a hub here. Since they're half duplex, if one person is talking, everyone else has to listen. So we don't really use this kind of access anymore, but they're waiting to see contending who can be on the line at that time. Controlled access is each node has its own time. This is the ring topology that we talked about. So it's basically like, I equate it to when you're playing poker and the dealer's changing. The dealer has the dealer chip, it's their time to deal. The round is over, the dealer chip moves to the next person, left or right. And then it's their person's time. So they have a token of some sort that says it's your turn. And then when the token goes away from you, you can't talk anymore. So that's what controlled access kind of looks like. They're waiting on their turn to talk, and when they're not talking, they have to listen to see if anybody else is. So here's what contention-based access kind of looks like. So PC1 has an Ethernet frame to send to PC3. PC1's NIC is going to determine, hey, is anybody else talking, or is it my turn to talk? If it doesn't detect any kind of signal on the line, then it will assume that the network is available and they can talk. So they're going to send out a frame, the hub's going to receive the frame and it's going to repeat it out all the other ports. If another device like PC2 wants to transmit, but it's currently receiving something, it has to wait till the line is clear. So that sounds like it works, but when you talk about how much we move on a network, that's going to take quite a while. Waiting on everybody else to talk so that we can go get a web page or something is not going to be desirable at all. And here all devices attached to the hub, again, are going to receive that frame out. If two devices transmit at the same time, if two different devices listen on the line and nobody's talking and then they try to transmit, we have what we call a collision. So both devices are going to detect that there was a collision on the network. In wireless, we use what we call CSMA-CA, Carrier Sense Multiple Access Collision Avoidance. So this is the router's way of saying, I'm going to talk and this is how long I'm going to talk. This is how big this data is that needs to move from me. So everybody stops talking for that amount of time because they listen to what the router said. Then everybody can start transmitting again. Wireless handles this a little different. A frame has some parts to it, so we call these headers, right? There's the header at the beginning that's got start and stop indicators that basically says this is a pattern of bits that tells you that a frame is here. So listen to the rest of this because it's all part of the frame. The addressing, so that's the source and the destination. At the frame level, everything is in MAC addresses. So that's going to look like a MAC address. The type identifies the protocol in the field. That's probably going to be something like Ethernet 2. The control, if there's some sort of flow control that we talked about in Chapter 3 a little bit, like quality of service, that's where this will come up. Then there's the actual data, the ones and zeros of the thing that you're sending. Then there's error detection. So it can tell you if there's been an error, like something didn't transmit over the line correctly, but it can't actually do anything about it. That comes up in higher layers. But it can say, wait, something went wrong with this data along the way, so don't trust it. Ones and zeros got messed up. That's generally what a frame looks like when you break it down. So the frame stays with a piece of data all the way to its destination. So from router 1, starting with PC1 over there, you see we've got L2, layer 2. Then it moves over the router from router 1 to router 2. We still have the destination and the source MAC address or the NIC address in that packet. And then when we move all the way to the final destination, to the web server, that data still stays with it as it moves through the web. Okay, any questions?